Image generation has long fascinated us, but how do you teach a computer to conjure a photorealistic image from thin air or from a text prompt?
It feels incredibly powerful. We've seen GANs, but they can be tricky to train. What if there's a more stable, principled way to achieve similar results?
That's exactly the question denoising diffusion probabilistic models, or DDPMs, began to answer. This paper, a foundational work, significantly advanced what was possible at the time by exploring a new class of generative models.
So, denoising diffusion probabilistic models. That's a mouthful. What's the core idea behind it?
At its heart, a DDPM is a latent variable model inspired by considerations from non-equilibrium thermodynamics. Imagine a physical process where particles spread out, like a drop of ink in water.
Like a drop of ink spreading in water? It starts concentrated and then diffuses everywhere, becoming uniform.
Exactly. DDPMs reverse that. They model how to unspread or undiffuse noise to reveal a clear image. It's like finding the original ink drop, but unlike a physical ink drop where molecules are perfectly traceable, here we're dealing with a statistical process. We don't perfectly find the original noise, but rather learn to predict and remove it.
So instead of creating order from scratch, it learns to reverse a process that destroys order? That's counterintuitive.
But it works remarkably well. This paper demonstrated high-quality image synthesis results, which pushed the boundaries of what was possible at the time.
It says they achieved state-of-the-art FID scores. That's a strong metric for how real generated images look.
A key piece of this puzzle is a connection between diffusion models and Langevin dynamics. This is a concept from statistical physics, describing systems in thermal equilibrium, often used to model particle movement with random forces.
Physics showing up in machine learning again. Does this mean they're using physical simulation to generate images?
Not directly simulating physics, but drawing inspiration. Langevin dynamics provides a mathematical framework for gradually transitioning between states, which is perfect for adding or removing noise step by step. It helps ensure that the denoising process remains stable and moves towards a probable data distribution.
So it's more about the mathematical framework than the actual particles, a way to formalize the iterative unspreading process?
Exactly. The big picture is taking a noisy image and progressively making it clearer. Let's see how that diffusion process is formally defined, starting with how noise is intentionally added.
All right, from high-level concept to how the noise actually gets added and removed in a structured way.
This blog post from Lillian Wang breaks down the core ideas beautifully. It states, diffusion models define a Markov chain of diffusion steps to slowly add random noise to data. This ensures the process is controlled and predictable.
A Markov chain means each step only depends on the previous one, right? So it's not looking back at the entire history of noise, just the state right before?
Precisely. The forward diffusion process starts with a clean image, x0, and gradually injects Gaussian noise over many steps, t. Specifically, at each step t, we get xt equals the square root of 1 minus beta t times xt minus 1 plus the square root of beta t times epsilon, where epsilon is noise sampled from a standard Gaussian. The beta t values are part of a variance schedule that dictates how much noise is added at each step.
So x0 is our clear image, and then x1 is slightly noisy, x2 noisier, until xt is essentially pure noise, and that formula ensures the noise addition is controlled?
That's it. We add small amount of Gaussian noise to the sample in t steps, creating a sequence of increasingly noisy samples. Think of it like taking a photo and repeatedly scratching it. While scratching removes detail, Our process adds a specific type of noise, Gaussian noise, which has predictable statistical properties, making its reversal learnable. A real scratch might be harder to unscratch.
And eventually, after enough steps, you can't tell what the original photo was, just random pixels. But because it's Gaussian noise, there's a mathematical structure to it that we can exploit.
A crucial property here is that we can sample xt at any arbitrary time step t in a closed form using reparameterization trick. This means we can directly compute xt from x0 and noise epsilon as xt equals the square root of alpha bar t times x0 plus the square root of 1 minus alpha bar t times epsilon, where alpha bar t is the product from I equals 1 to t of 1 minus beta I. We don't have to simulate each step to get xt, which is a huge computational advantage.
That's convenient. If we want x50, we don't need x0 through x49. But wait, what does reparameterization trick mean in this context? Does it just speed things up, or is there a deeper reason?
That's a great question. The reparameterization trick here doesn't just speed up sampling, it's essential for training. By expressing the noisy xt as a deterministic function of x0 and a standard Gaussian random variable epsilon, we make the entire forward process differentiable. This allows us to backpropagate gradients through the stochastic parts of the model during training, which is fundamental for learning.
So it turns a sampling operation into a transformation, which means we can optimize the neural network that predicts the noise. That makes perfect sense for machine learning training.
Exactly. The image gradually loses its distinguishable features as the step t becomes larger. The key insight is, if we know precisely how this noise was added, can we reverse it to restore the original image?
So the goal is to learn the unscratching process, going from random pixels back to a recognizable image by learning to remove the Gaussian noise step by step.
Yes, the reverse diffusion process. If we can learn to accurately predict q of xt minus 1 given xt, that is, what the image looked like one step before it got noisier, we can go from pure noise back to a clean image. This is the generative part.
But that conditional probability, q of xt minus 1 given xt, seems like it would be incredibly complex to model directly. How do you predict the exact previous state?
You're right. The source states we cannot easily estimate q of xt minus 1 vert xt because it needs to use the entire dataset. This is indeed the central challenge for DDPMs. Directly computing this reverse probability is intractable.
So we can define the forward process with simple math, but the reverse process, which is what we actually want for generation, is intractable. This seems like a dead end.
That's where the core innovation of DDPMs comes in. The key is to find a clever way to approximate this intractable reverse step. Let's look at how they achieve that by simplifying what the model needs to learn.
Okay, so the intuition is clear. Add noise, then reverse. Now, how do we learn that reverse process effectively despite its intractability?
The article points out a crucial detail. The reverse conditional probability is tractable when conditioned on x0. If we hypothetically knew the original clean image, x0, reversing the noise addition would be mathematically straightforward.
But for generation, we don't have x0. We're trying to create it from noise. How does knowing this theoretical tractability help us in practice?
It turns out the tricky part is predicting the mean of that reverse step. DDPMs cleverly reparameterize the Gaussian noise term instead to make it predict epsilon t. Instead of predicting the mean, mu theta of xt directly, the model learns a neural network f theta to predict the noise epsilon that was added to x0 to get xt. With this predicted noise epsilon hat, We can then estimate the denoised image and, in turn, the mean of the reverse step. This simplifies the learning target dramatically.
So instead of directly predicting the denoised image, the model predicts the noise that was added to get to the current state. That sounds much simpler.
Exactly. Imagine you have a moderately noisy image. The model learns to predict just the noise component that, if removed, would make the image slightly cleaner. This noise is what obfuscates the original signal.
And if it removes that predicted noise, you get x sub t minus 1. Then it repeats the process, predicting the noise in x sub t minus 1 to get x sub t minus 2. So it's a series of noise predictions and subtractions.
Precisely. The model learns to predict epsilon t. Once we have that predicted noise, epsilon theta of xt comma t, we can use it to reconstruct the mean of the previous, less noisy step. Specifically, we would like to train mu theta to predict mu theta t equals 1 over root alpha t times xt minus 1 minus alpha t over root 1 minus alpha bar t times epsilon t. This gives us the mean for the Gaussian distribution from which we sample x1.
So the actual reverse sampling step involves taking the current noisy image xt, using the predicted noise epsilon theta to calculate this mean, mu theta t, and then sampling xt minus 1 from a Gaussian centered at mu theta t, with a specific variance. That's the explicit mathematical procedure for denoising.
Exactly. We train a neural network to approximate this noise prediction function. It takes a noisy image, x sub t, and the current time step, t, which tells it how much noise to expect, and outputs the predicted noise, epsilon sub theta of x sub t, t.
So it's essentially a denoising autoencoder, but specialized to predict the noise itself, not the clean image directly. That's a subtle but powerful difference.
The training objective for this network is surprisingly elegant. This section shows the final simple objective is to minimize the squared difference between the actual noise that was added in the forward pass and the model's predicted noise. Mathematically, we train the network to minimize L equals E of t, x of 0, epsilon into epsilon minus epsilon theta of x of t, t squared, where epsilon is the true noise added to x of 0 to get x of t, and epsilon theta is our model's prediction.
That's much simpler than what I would expect for a complex generative model. Just a mean squared error on the noise, averaged over different time steps and samples. It feels very robust.
This leads to an important connection with noise condition score networks, NCSN. While they seem different on the surface, DDPMs can be shown to be closely related to score-based generative models. They are essentially performing score matching.
We haven't covered score matching, but it sounds like finding the direction to clean up noise, or figuring out how probability density changes.
In essence, yes. The score function is the gradient of the log probability density of the data, nabla xt log q of xt. It points in the direction of increasing data density. The model's predicted noise, scaled, approximates nabla xt log q of xt. More precisely, the predicted noise epsilon theta of xt is related to the score by nabla xt log q of xt approximately equals minus 1 over square root of 1 minus alpha bar t epsilon theta of xt. By predicting noise, the DDPM is implicitly learning this score function.
So, by predicting the noise, the model is implicitly learning the gradient that pushes noisy data towards higher probability, cleaner states. That's a beautiful mathematical equivalence.
Precisely. This allows DDPMs to generate high-quality images. However, operating directly in pixel space, especially for high resolutions, is incredibly slow and resource-intensive, requiring hundreds or thousands of sequential denoising steps for every single image.
The computational bottleneck. Generating a 1024 by 1024 image pixel by pixel across thousands of denoising steps sounds like a nightmare, especially for interactive applications.
That's where latent diffusion models, or LDMs, come in. The core idea is to move the computationally intensive denoising process out of pixel space into a more manageable one.
So instead of denoising pixels directly, we denoise something else? A compressed representation that's easier to work with?
Exactly. This paper proposes to apply them in the latent space of powerful pre-trained autoencoders. This improves efficiency dramatically because the latent space is much smaller than the original pixel space.
We built up autoencoders in TCM-NNNNNN. The encoder compresses the image into a latent representation, and the decoder reconstructs it. So LDMs do the diffusion process on the compressed version and then use the decoder to get the high-res image back?
Precisely. The autoencoder acts as a perceptual compression model. The diffusion model learns to generate semantically rich latent representations, and the decoder translates these back into high-fidelity images. This means the expensive iterative denoising steps happen in a lower dimensional space, saving significant computation.
That's brilliant. It's like working with a high-level summary of an image rather than every single detail, then expanding that summary at the very end. The diffusion model focuses on composition and style in the latent space.
Beyond just efficiency, LDMs also introduced a powerful way to control the generation. They introduce cross-attention layers into the UNet backbone, enabling control via various modalities like text, bounding boxes, and segmentation maps. This means we can condition the image generation not just on a vague concept, but on precise inputs like text prompts or even structural information.
So the model in the latent space isn't just generating any image, it's generating an image guided by our input. This is how you get those amazing text-to-image results, by feeding the text embedding into the cross-attention layers during denoising.
Exactly. The cross-attention mechanism allows the latent denoising process to pay attention to relevant parts of the conditioning input at each step, ensuring the generated image aligns with the prompt. The conditioning information, like text embeddings from a large language model, guides the model towards the desired output. It's a key reason for the surge in controllable generative AI.
This integration of autoencoders, diffusion, and cross-attention in the latent space really feels like the complete package for powerful, high-resolution image synthesis.
Even with latent diffusion, it's important to note that generating a single image still involves many sequential denoising steps, making inference much slower than single-pass generative models like GANs. Training these models also remains computationally intensive, though significantly less so than pixel space DMs. It's a trade-off: higher quality and control for increased computational costs during inference compared to some alternatives.
So while LDMs address the pixel space bottleneck and offer incredible control, the iterative nature still means a trade-off in speed compared to some alternatives. It's a powerful tool, but not always the fastest. Understanding these limitations is as important as appreciating their capabilities.